So the next topic is something called integer memory safety vulnerabilities. We're going to look at another way where we can exploit dangerous C programs or vulnerable C programs to execute code that the attacker wants to execute. So here's a piece of code. Let me walk you through it. So it says, I'm going to pass in a character array. And remember, in C, the way that you pass in character arrays as an argument to functions is you pass in two things. First, you pass in a pointer, that is the address of where the array starts. And then you pass in how many things are in the array. So it's kind of annoying, but this is the way that you do arrays in C. You always pass in a pointer for where the array starts, and then a second argument for how many elements are in the array. And the reason to do this is because, remember, C doesn't do bounds checking. Just by passing in a pointer, I have no idea where the array starts and ends. So I pass in the start of the array, and I pass in how many bytes or how many elements are in that array. And usually when you pass these two things in, we usually will assume that they match up with each other. So yeah, I guess there could be cases where the attacker lies about the length. But in general, we'll assume that these two things are linked to each other somehow. So when the attacker passes in an address, they also pass in the correct corresponding length. And that's something that differs in different pieces of code. I'm kind of going on a digression here, but the punchline is these two arguments tell us the input array. It's the data and the honestly reported length. OK, so what comes next? Then I create a buffer of size 64 bytes. And I say, if the attacker wants to input more than 64 bytes, that is, if length is greater than 64, I'm going to return from the function. You cannot write to this character array if you input more than 64 bytes. But if you input less than 64 bytes, then I'm going to copy data from the argument data into the buffer, and I'm going to copy length number of bytes. So whatever the attacker or the user inputs, I'm going to copy it into buffer, but only if it's less than 64 bytes. So at first, it seems like this is totally fine. We have a check, and the check says if the attacker inputs more than 64 bytes, they're just going to run into this if case, and the function will return, and the attacker cannot overwrite past the end of buffer. So this seems totally fine, as long as we assume that the attacker is honestly reporting the length, and we'll assume that for this slide, then there's no problem. Or is there? So if I stare at this more carefully, there's actually a really subtle bug. And every time I show people this, it's something they haven't thought of. So what if this array is actually really big? And I mean really, really big. I'm talking something like, I don't know, like FFFF. That's a really big character array. So then if I pass in something like FFFF, or rather an array of length FFFF, that's a really big character array. So I can pass in that array. I'll pass in that really large length. And I'm still honestly reporting the length, so I'm still matching my assumption. But take a look at this argument. This argument says int. And remember, integers can be positive or negative. So if I pass in an array, and I pass in the length, and the length just so happens to be hex FFFF, that's a really big number. But if I interpret that number as a signed number, that is an integer that could be positive or negative. And if you think back to CS61C and how we represent things as 2's complement, well then, when I pass in something like FFFFFFF, that's actually going to be interpreted as what? -1. FFFFFFF, if you interpret it as unsigned, it's a really big number. It's the length of this big array. If I interpret that same sequence of ones and zeros as a signed number, I get -1. Well, that's kind of weird. What happens if I go through this code with -1? That's not something I had thought of before. If I go through this code with -1, the code checks, is -1 greater than 64? No, that's not true. So that means this if case doesn't run. And so I go to this memcopy. And now I'm going to copy from data into buff. And I'm going to copy length bytes. And again, I'm copying the bits FFFFFFF as length. So throughout this entire piece of code, length is always FFFFFFF. It's the exact same sequence of ones and zeros. The only difference is how we're interpreting it. Do we interpret it as a signed number, in which case this sequence of bits means -1? Or am I interpreting it as an unsigned number, in which case this sequence of bits represents a really big number? So initially, when the attacker passes in their array, they're interpreting those f's as a really big number. But once I enter this function, because this argument was defined as int, suddenly this function is thinking about signed numbers. So when it sees all f's, it thinks -1. Is -1 greater than 64? Nope. So I move on to this memcopy line, and now I go into memcopy. And if I open up my man pages and I look for the definition of memcopy, memcopy takes in something called the size t, which is once again an unsigned type. So what that means is when I take this FFFF sequence of 1s and 0s and I call memcopy with it, memcopy is going to read it as an unsigned number. So suddenly memcopy is once again thinking unsigned, and it says I want to copy a huge amount of bytes from source to destination. And once again the attacker is able to overwrite past the end of buffer. This is a really tricky exploit to even notice, but to summarize it once more, the problem is that this sequence of bits that we called len is sometimes being interpreted as a signed number, sometimes being interpreted as an unsigned number. So inside this code, it's being interpreted as signed, and that allows us to bypass this if check. But once I get into this memcopy, suddenly it's being interpreted as unsigned again. And that's a problem because now memcopy is going to treat this unsigned number as a really big number and copy a lot of bytes from source to destination. So this exploit is appropriately named signed unsigned vulnerabilities. So that's another really sneaky thing you can do to try and write past the end of a buffer. Even if the programmer seems like they've patched the issue could still be there. So it's really tricky to catch bugs like this. But again, the key problem is that we're taking the same sequence of 1s and 0s and switching between interpreting those 1s and 0s as a signed number or an unsigned number. And that could allow us to bypass some of these checks that the attacker included. OK, so how do you fix it? Well, here's a potential fix. So here the fix is I now have to read len as a size t. That's an unsigned integer type. So because now this is an unsigned integer type, everyone is using the same interpretation. When I pass len into this safe function, it's interpreting len as an unsigned number. When I pass it to memcopy, it's also thinking in unsigned terms. So everyone's thinking in terms of unsigned, so now the check is doing what it's supposed to do. But it's a really sneaky bug that you can easily accidentally introduce into your code.